everybody. So this is the third video of the videos on repeated measures ANOVA. Remember that the study that we are analyzing is the study of the researcher who's interested in understanding whether his behavioral intervention is helping to reduce distractibility levels in children with ADHD long term. So he took 4 children who have ADHD, measured them at baseline, administered some sort of therapy for 3 months, measured them again, and then after that, measured them 6 months later. So it's a repeated measures design simply because we're taking the same group of individuals, measuring them repeatedly. So those sample means are going to be related. And because of that, we're using a repeated measures ANOVA rather than an independent samples or a one-way ANOVA. So we're to the point in our 6 steps of hypothesis testing where we have to calculate the test statistic. And like the other ANOVA, I'm not going to have you actually calculate it by hand. You're welcome to, but I'm not going to teach you how to do it. But what I want you to understand is the ANOVA table and what the values mean in the ANOVA table and where everything is coming from. Because what ANOVA does behind the scenes, of course, is parse out all the sources of variability. So this is the table for the repeated measures ANOVA. It's very similar to the one-way ANOVA in that you have the source of variability. And again, the source of variability refers to the variability in the scores of the dependent variable. All right, where is the source of the variability coming from? We also have the sums of squares, degrees of freedom, mean square, and the F ratio. Again, F refers to Fisher, and Fisher is the individual who came up with the ANOVA, the analysis of variance. So that's the F statistic that we're solving for. So we have the same number of columns that we have with the one-way ANOVA. The thing that's different are the rows. Whereas in the one-way ANOVA, we only have 3 rows. We have the between groups variability, we have the within groups, and then we have the total. In our within groups or repeated measures ANOVA, we have 4 rows. And think back to the very first video where I compared side by side how the 2 ANOVAs are parsing out that variability differently. So with the one-way ANOVA, it's really parsing out the variability into the total amount of variability of the scores based on the variability to the treatments and then the variability due to just error in general. And in the repeated measures ANOVA, you still have the total amount of variability. And from that, we can see the variability due to the treatments, but then the variability due to error is parsed out further into variability that's due to the subjects, and then the variability due to residual or the error. So we have just a little more detail there. So when we look at this table, we have those 4 rows, and really the rows that are most important when calculating out that F statistic is the treatment, okay, the amount of variability due to the signal, due to that independent variable, and then the amount of variability due to that noise, due to the true noise. After we remove out the individual variation, the variation due to the people, what is that true noise, the other random factor? So that's that residual, so the signal to noise ratio. So this is kind of how you find everything mathematically. Now let's look at the numbers. So long story short is that for this example, the F ratio is 18.72. So how are we getting that? To get any value of F, it's always a mean square over another mean square, the signal to noise. So in this case, it's the mean square for our treatment over a mean square residual. That's how we get the 18.72. So how do we get the 52.59 and how do we get the 2.81? Well, a mean square is always found by getting a sum of square divided by a degree of freedom. So the sum of square for treatment divided by degrees of freedom, so 105.17 divided by 2 is 52.59. and 1683 divided by 6 is 281. All right, that's how we get those mean squares. Now, of course, the total sums of square 430.67 is the product of these three values combined, and 11 degrees of freedom is a product of those three values combined. Why is this important? Because you might be provided with a table like this with a couple of values omitted, and I might ask you to plug those in. So make sure that you understand that. All right, so the very last part of the 6 steps is always interpreting the results. And we always ask ourselves 3 questions. First of all, most importantly, was our null hypothesis rejected? And to answer that question, we simply compare our observed value of f to the critical value of f. So in this example, our f value was 18 something and our critical value was 5 something. So our observed is greater, so we say yes, we did reject the null. The means are statistically different from one another. So when we have a statistically significant effect, we go ahead and answer 2 other questions. First of all, what is the effect size? How big is the effect? What is the impact of that independent variable on the dependent variable? And then lastly, where is that effect found? Because the ANOVA only tells you, hey, something's going on. It doesn't tell you where that something is happening. So let's look at the effect size. We're going to use eta squared. Eta squared is right here. And to find that, we simply go to our ANOVA table and we find our sums of squared treatment divided by total, and we get a percentage. And in this case, we find that it's 24.42%. It's a medium to large effect size. So that simply tells us that this behavioral intervention has a pretty big effect on behavior, have a pretty big effect on reducing distractibility. The last thing that we do is find which means are different from one another. And just like the one-way ANOVA, we're going to use a Tukey test. It's a post hoc test. And it's going to tell us exactly which means are different from one another. And again, why do we do this? Well, a Tukey test is going to tell us which means are different while controlling for type 1 error. So to find that honestly significant difference, we have to find Q. Q is a value we get from the appendix in the back of the book. To find that, we have to figure out what K is. K is the number of groups that we're comparing. And in this instance, we have 3 means that we're comparing. We also need to figure out our mean square residual, which we find from our ANOVA table, and then the number of cases in our groups, and that was 4. So when we put that all together, we find that Q in the back of the book was 4.34. We put the mean square residual 2.81 in our formula, as well as 4 cases. We find that the honestly significant difference is 3.64. Who cares? What does that mean? All that tells us is that for any 2 means to be different from one another, they have to differ by 3.64. So remember, we have our 3 treatment conditions: baseline distractibility, after treatment distractibility, and then 6-month follow-up. All that means is that those 3 means have to differ by this in order for them to be statistically different from one another. So let's look at these comparisons here. And these are just mean differences. So pre-treatment to end of treatment, the means differ by 7.25. That's different than 3.64. So those 2 means are statistically different. Pre-treatment at 6 months follow-up, those are not different. So what that tells you is that even though this behavioral intervention did reduce distractibility significantly, it didn't do so long term. And if you look at pre-treatment to the 6-month follow-up, which we just did, there's no difference. You also see the end of treatment to the 6-month follow-up, which is right here. There is a difference. So you see that there's a significant rebound, if you will. So the very last thing that we do with our 6-point interpretation, 6 steps, is our 4-point interpretation. In this case, it's always restating the purpose of the study, which is to determine whether a behavioral intervention is effective in reducing distractibility. In this particular study, it was found that there's a significant effect of this treatment on distractibility levels. What was found was that although there was a significant decrease after treatment, it did significantly increase after it was terminated. Even though it did not make it back up to baseline levels, statistically it was no different than baseline. So what this really tells the researcher is that in order for this to be effective long term, is that you have to have some sort of perhaps intermittent type of training. That's what I would kind of say. So anyway, that is the repeated measure ANOVA. Really the only different thing from the one-way ANOVA is that we have the same sample measured at different points in time. And because of that, mathematically, we have to approach it differently. So again, if you have any questions, let me know. Send me an email at asikorsky@tamet.edu. Hope you guys are doing well, surviving, the shelter in place and social distancing and all of that. I know it's really tough. And I applaud you guys for, toughing it out in learning through YouTube videos and, going at it on your own. So again, don't hesitate to reach out and let me know if there's anything else I can do for you guys. As always, take care. Bye-bye.